Alright, so I'm going to start off looking at 6.4. Now, we went into a lot of depth graphing sine and cosine. We studied all the different transformations, and we spent 3 days just on sine and cosine. We're not going to go into as much depth with the other trig functions. We're going to spend 1 day on them, kind of get the idea of what they look like, and that's pretty much it. We also are not going to do a lot of sketching by hand. Okay, we're going to do more sketching on the calculator than we did in section 6.3. So the first graph I want to take a look at is tangent. And if you remember, tangent is equal to something. Does anybody remember what two trig functions you can divide and it gives you the tangent?
Sine by cosine.
You can divide sine by cosine.
So what was this unit called?
6.4. Graphing sine, other trig functions. So secant, cosecant, tangent, cotangent. All right, so now we know a lot about sine and cosine. So let's think a little bit about this. I want to know when the tangent is equal to 0. What would have to happen in this fraction for the tangent to be 0?
Sine has to be equal to 0.
The sine would equal 0. Right? So the tangent function will cross the x-axis whenever sine crosses the x-axis. Whenever the sine is 0, the tangent is 0. So tangent is 0 when the sine is 0. So let's think about sine for a minute. Here's 3 places where sine is 0. What's this first one? 0. How about the one at the end? 2 pi. And the one in the middle? Pi. So there's 3 places where the tangent function would be 0. Basically, if you summarize it, it's every multiple of pi. 3 pi, 4 pi, 5 pi, 6 pi, and so on. And negative. Negative 2 pi, negative 3 pi. But it's every integer multiple of pi. Now, the other functions that we drew, sine and cosine, they were continuous functions. Tangent is not. Because something could happen with cosine that would cause the result here to not be a number. The cosine could equal 0. And what's going to happen whenever you try to divide by 0? You get a vertical asymptote. So the tangent function will have an infinite amount of vertical asymptotes, specifically everywhere that the cosine is 0. All right. So let's think about cosine for a second. Here's our graph of cosine. Does anybody remember the x values for those 2 points?
Pi over 2 and
Pi over 2. And
3 pi over 2.
3 pi over 2. So tangent will have vertical asymptotes at every odd multiple of pi over 2. 1 pi over 2, 3 pi, 5 pi, 7 pi, 9 pi over 2, and so on. It's every odd multiple of pi over 2. And usually once we get an asymptote, something like this, we test a point that's very close on the left and very close on the right. And usually when we get close to the asymptote, what happens to our value?
They either extends towards infinity.
Right, it either goes like way up here or
Way down.
way down. Usually it's one side is up very high and the other side is very low. So knowing where the graph crosses the x-axis, knowing where the asymptote is, and testing a point on each side of the asymptote, we should be able to get a pretty good picture of what tangent looks like. And then once we have tangent, well, cotangent would be very similar, but cotangent is tangent flipped. So the sine and cosine would switch places. Let's start with tangent. Okay, Does everybody have that first? And I'm going to have to keep coming back to this so we can remember where the zeros are and where the asymptotes are. Can I do it on the screen? Yeah, I'm going to try to do it at the same time. Let's go like this. Okay, so I wrote down the asymptotes that we get from where cosine is 0, pi over 2, 3 pi over 2, 5 pi over 2, and so on. So let's draw those in. Pi over 2, 3 pi over 2. Okay, good enough. And the zeros, where it crosses the x-axis, are 0, pi, and 2 pi. Now remember, it's going to go on forever, so we just want to get an idea of what one section of tangent looks like, which is really going to be in between two dotted lines, and then we'll know what all the sections look like. So I have a 0 here, here, and here. I'm going to focus on I'm going to call this like section 1 and section 2. I'm going to focus on drawing in between section 1 and 2. It's going to look identical. All right, so now let's put in tangent, and let's get a value that's close to those two asymptotes. So let's put in tangent. Make sure we're in radians, because that's what my x-axis is in. All right, now I can't put in pi over 2 or 3 pi over 2, because we know those would be undefined. But we want to put in a value just to the left of pi over 2. So pi over 2, the easiest way to do it is just go like this. Take pi over 2, and if you want to go to the left of something, would you make it smaller or bigger?
Smaller.
Smaller. Let's just make it a little smaller. We'll subtract 0.01 from it. And if we do that, we're up at 100. So a little smaller, way up here. And that was just to start the pattern off. You can probably guess what's going to happen on each side. It's going to alternate. So let's do pi over 2, and let's just add a little bit. Now you can see I'm at negative 1,000. So I'm way down. That's going to be the behavior on each side of the dotted line. Up on the left side of it, down on the right. So let's do it here. Up on the left, down on the right, up on the left, down on the right. Now focus in section 1. Okay, we got to connect all 3 of those dots, and we have to stay as close to the asymptote as we can until we have to curve through the 0, but then we're stopped again by another asymptote. And that's what tangent looks like. Same thing here. Stay close, it's going to curve, it's going to go up. So what you're looking at there, that's 2 sections of tangent. I do zoom 6. Well, you're looking at half a section and then it kind of cut it off. And the 2 sections that we did are these 2 right there. All right, any questions on it? So that's what tangent looks like. So very different than sine and cosine. Still periodic, meaning it repeats itself. We're going to see how often it repeats itself. Let's. Does anybody remember for sine and cosine how often it repeated? What was the normal length of the period? 2 pi. So let's go 0 to 2 pi, and let's see what happens. Now I know it's a little weird because one of them is broken up, but that's 0 to 2 pi. How many cycles are you looking? That's not a picture. Okay, likes the last one. So you're looking at half a cycle, and a full cycle. So how many cycles are we really looking at there?
2.
That's 2 cycles from 0 to 2 pi. So what would one cycle be from what to pi. So this is a little bit different. Normally when you go 0 to 2 pi, you'd see one cycle. With tangent, you're seeing two cycles. So that means the regular period of tangent is pi. So tangent naturally cycles faster than sine and cosine. Now, the other thing we have to kind of decide on here is how many asymptotes are there per cycle? It's kind of like armrests, right? Like a movie theater. We can't say that one armrest belongs to both, right? It either is going to belong to the one that's to the left of it or the one that's to the right. So when we talk about how many asymptotes there are per cycle here, there's only one. There's one asymptote per cycle. I would say that this asymptote belongs to cycle 1. This asymptote would belong to what I call 2. Right? But you just don't want to, you can think of it however you want to think of it. But the idea is to remember there's one asymptote per cycle, not 2. Because if you say there's 2 per cycle, then all of a sudden one cycle wouldn't happen because it would belong to the other. So that's tangent. And now cotangent is, what do we call that when we flip it? It's a reciprocal. So what's going to happen now is everything that was a 0 before is going to become a what? An asymptote. And everything that was an asymptote is going to become a 0. So before we had zeros at 0, pi, and 2 pi. Well, 0 pi and 2 pi are going to become asymptotes now. And there they are. 0, pi, 2 pi, those are asymptotes. And pi over 2 was an asymptote before. Now it's a 0. And if you check a point on each side of the asymptote, the curve switches. So for cotangent, you could think of cotangent as always having a negative slope. Cotangent curves down and to the right. Tangent is a positive slope. It goes up and to the right. And that's your graph of cotangent. It also has the same cycle as tangent. It naturally cycles every pi units. How would I graph cotangent? Because I don't have a cotangent. Well, I mean, I could do this.
Yeah.
I could do that, or I could just do 1 divided by tangent. That's easier. I could do cosine over sine, though. That would work. And if I set my window from 0 to 3 pi, how many cycles do you think you're going to see? 3. And this time, it's not going to break one up because the asymptote is the y-axis. So there's 1, there's 2, and there's your third cycle. So it cycles every 3.14 units. So we had some formulas that we talked about before called the periodic property for sine and cosine. And it said that if you had an angle like, I don't know, let's do it in degrees just to keep it simpler. Let's say you had the sine of 800 degrees. What can you do to 800 that would make it smaller and not change the answer? You could do the sine of 800, and you could minus 360.
You didn't minus it.
Nope, I did not minus it. So I minus 360 and I get the same thing. We can add and subtract 360 as many times as we want, and it will not change the answer to a sine or cosine problem, because that's the cycle of sine and cosine. What do you think we could do with tangent?
Add 180.
We could add or subtract 180. So the tangent of 190 would be the same as the tangent of what? 10. Because they cycle every 180 degrees. Now you can add or subtract multiples of 180, or if you're doing it in radians, you would be adding and subtracting multiples of pi. So this just gives us an easier way to think about a tangent or cotangent problem. If the angle is too big, we can make it smaller by subtracting pi. If it's negative, we don't want to deal with a negative, we can add pi. But you can't add half pi or like a quarter pi. You got to add an entire multiple of pi or an entire multiple of 180. Okay. Any questions on that? So, does anybody remember the formula we used for calculating the period for sine and cosine? It was t equals,
Is that 2 pi over b?
yes, it was 2 pi over b, where b was the number that's in front of x inside the parentheses. This is for sine and cosine. That's going to be different with tangent and cotangent. What do you think the 2 pi would be? Just pi. The number in the top is the original period. For tangent and cotangent, that would be pi. And I think I write that down. Yeah, I'm going to write that down in a minute anyway. But it's going to become pi over b. All right, so transformations.
Oh, already?
What do you think is different about transformations here compared to everything else we've studied all year? Nothing. They are exactly the same. There is no difference when you do a transformation with tangent or cotangent as compared to anything else we've studied. So adding or subtracting inside, that's your phase shift. And phase shift is just a fancy way of what? Saying that's your horizontal shift. B changes the period length.
Wait, let's say c plus an.
Tangent.
Oh. My bad.
Yeah, I can see that. Yeah, C times T. B is your period change. And a period change does what to your graph?
It's a horizontal stretch.
Horizontal stretch or compression.
And you can flip it too if it's negative.
Yep. If B was negative, it would flip it. C, I'm trying to think. C, I don't want to call it that. What does C do?
Stretch.
That's your vertical stretch. I don't want to call it amplitude because amplitude is usually like a defined point where the graph stops and you can measure a distance. The graphs of tangent and cotangent, they don't stop. They just keep going up forever and down forever. So they're infinitely tall. So I've never really heard tangent referred to as having an amplitude. So we're going to just call that the vertical stretch. And D is the vertical shift. If D is positive, it would move negative, down. And if A is positive, it would move left. And negative would be right.
So period change is horizontal stretch.
Yep. And the bigger that you make B, what happens to the graph?
The
The more compressed it gets. The bigger and bigger and bigger you make B, the more and more squished it gets. And the smaller you make B, like if you make B a fraction, like 1/5, the smaller it is, the more it stretches. Okay, so there's our formula that I usually put up for transformations. And this is the formula for calculating the period of tangent or cotangent. It's t equals pi over b. Most trig functions are 2 pi over b. And by most, I mean sine, cosine, secant, and cosecant. But tangent and cotangent are the only two that use pi over b. And remember, b is the number in front of x. So even though we're not going to do a lot of sketching by hand, one thing they may ask you for is the asymptotes. So what I'm going to show you next is how do you find the asymptotes for really any trig function, not just tangent and cotangent. We're going to learn secant and cosecant also have asymptotes. But this is how you find asymptotes for any trig function. But it does apply specifically to tangent and cotangent because that's what we're looking at right now. The first step is to find all the asymptotes in one period of the original function. Now, for tangent and cotangent, how many asymptotes did we say that there are in one period? One. So, step one would basically mean knowing numbers like 0, pi, and 2 pi for cotangent. Or knowing pi over 2, 3 pi over 2, and 5 pi over 2 for tangent. Okay, it would just be knowing those numbers. Nothing you have to calculate. Now, step two is you take one of those original asymptotes that you found, you set it equal to the argument, and then you solve. Remember, the argument is this. You're going to set what's inside that box equal to one of the original asymptotes, and then solve. Now, how many asymptotes are there if you could zoom out forever in the tangent function? There's infinitely many. So we can't write every single one. But we do know that they occur regularly. They occur in a predictable way. How often is an asymptote going to repeat in general? It's going to repeat every period, whatever the period is. Once we know where the first one is, and we figure out in step two where it shifts to after the transformation, then all we have to do is say that that asymptote repeats every single cycle. And that's the last step. So to say that an asymptote repeats every single cycle, you have to find one of them. That's from step two. And then put this on the end, plus the period times n. This period times n represents you could add any multiple of the period to an asymptote and get another one. And this asymptote that you start with from step two, it doesn't really matter which one you start with. You can start with any original asymptote. I usually start with the first positive one, that's the smallest. And the reason you could start with any asymptote is you can kind of think of it like, pretend like you set an alarm to go off every single hour starting at 3 o'clock for the rest of your life. And then somebody else set an alarm to go off at 2 o'clock every single hour for the rest of their life. Well, your alarms would be going off at exactly the same time. It doesn't really matter that you started at 1 and the other one started at 3. You're still going to get the exact same alarms repeating at the exact same time forever if you zoom out and look at all the alarms forever. Any question on that idea? So it doesn't matter which original one you start with, you just need to start with one and say that it repeats forever. All right, let's try this one. So it says find the period, and then find a viewing rectangle that shows exactly 3 cycles.
Pi divided by 2.
So in this case, the period is going to be pi divided by 2. So there's the period. And let's say we want to show exactly 3 cycles. How wide does my window have to be to show 3 periods?
3 pi over 2.
It has to have a width of 3 pi over 2. So what's one way that I could get a width of 3 pi over 2? I could go from 0, yep, to,
3 pi divided by 2.
yeah, that's the easiest probably to do it.
We're in degrees right now.
Yep, so that's, I should switch back to radians. It's okay if you type it in like that, but you need to switch. But that 4.71 will stay there. At least it should. Yep. Thank you. And there's other ways you can do it. If you wanted to go like negative 3 pi over 2 to 0, that would work. If you went 1 pi over 2, or like 2, let's say you did, 1 pi over 2 to 4 pi over 2, I guess that would work too.
It's a lot more complicated.
But yeah, just pick the simplest one. And when you hit graph, you may break a cycle in the middle. Didn't say we couldn't, that's okay. But do we have 3 cycles there? Yeah. We've got 2 complete, and then a half makes 3 cycles. So there's your sketch. And here's the window that we used. Question on that? Let's try this one. So I've got 2 graphs, and I want to identify which one is 2 tangent x and which one is 5 tangent x. So you don't have to sketch it. You just have to know what the 2 and the 5 are doing. What type of transformation is the 2 and the 5? Yep. It's a vertical stretch. So one of them is going to be stretched vertically more than the other. So we're looking for which one looks like it's stretched vertically more. So which one do you think 2 tangent x is? The right one. Because the more and more you stretch it vertically, imagine like you had a piece of metal with like a bend in it, and you keep pulling on it, it's going to start to straighten out. So this one to me looks like it's stretched more. And this one not as much. Okay. Any question on that? Okay. Let's try, I want to go back to the asymptote thing for 1 second. We're going to practice more, but I want to try one with that first, with tangent. Because tangent's easier because there's only 1 asymptote per cycle. Now, let's take this one. Tangent 2x. Let's think of, for tangent, one of the original asymptotes. If you don't know, we can go back. But tangent has an asymptote. Let's take pi over 2. That is one of the original asymptotes. Pi over 2. So let's take pi over 2 and set that equal to the argument and solve. Okay, so pi over 2. That's the original asymptote. And what's the argument here? 2x. We're going to solve. So we're basically figuring out where this one asymptote is moving to in this transformation. And once we know where this one goes, all of them are going to do the same thing. They're all going to squish or stretch, whatever's going to happen. So where does this asymptote end up? Pi over 4. It's squished. It's squished by a factor of 2. So now we know that all the asymptotes, we can start from pi over 4. And you don't have to give me a specific number yet, but how often does an asymptote repeat?
Every pi.
In general. It repeats every period.
Oh, yeah.
So this is our new asymptote, and this is going to repeat itself every cycle. What was the length of the cycle here? Pi divided by 2. So we can write down that our asymptotes are now going to start at pi over 4, and they're going to repeat forever, left and right from that point, every pi over 2 units. So that's how we would write it. If this was degrees, we could say that our first asymptote is 45 degrees, and then we can keep adding or subtracting multiples of 90 and get asymptotes forever, left and right. But that's how you describe them all. Okay, and we'll do that again. But I wanted to do one with tangent first. All right, now let's think a little bit about secant and cosecant. What is cosecant? It's 1 over sine. Now, can the graph of sine ever equal 0?
Yeah.
Yes, it can. So if sine can equal 0, then what's going to happen in this fraction? It's going to have undefined values, which when you graph it means asymptotes. Now, think of sine. There's a cycle. Everywhere that sine crosses 0, crosses the x-axis, that's going to be an undefined value. Does everyone agree that this is one cycle of sine?
Yes.
Okay. How many times does that cross the x-axis?
3.
Well, it only crosses it once in that. Right? If it was like-
Well, remember, it goes forever.
Well, yeah.
So
It
crosses
it.
per cycle, how many times does it cross? 2. We can't say 3 because think of it like this. Here's a cycle. Here's a cycle. Each one of those boxes has to have the same number of x-intercepts. So if we say that this one is in this box, then we have to say that this one belongs to that box. We can't say that this one belongs to this box because now we have a problem. Now we're saying that there's 3 crossings in this box. But then in this one, well, you wouldn't count this one because you counted it here. So what are you going to say now? There's 2 in this box? You can't have 2 here and 3 here. So we say that there are 2 in every box. And I guess if you want to think of them, that way, that one would go over there. So this one belongs to this box. That one's right in the middle. And then this one at the end belongs to the next cycle. So keep that in mind. 2 asymptotes per cycle. So let me show you what this one looks like. So here's secant and cosecant. For cosecant, we get a 0 everywhere that sine is, or we get an undefined, we get an asymptote. Everywhere that sine is 0. Where is sine 0? 0, pi, 2 pi, 3 pi, 4 pi, and so on. For secant, we get an asymptote everywhere that cosine is 0. Cosine is 0 at odd multiples of pi over 2. So that's where we get our vertical asymptotes, the zeros of cosine. And here, it's the zeros of sine. And one cycle would basically look like this. For secant and cosecant, one cycle is a full U shape and an N shape. Or if you cut part of it off, whatever. But you have to have a full U and a full N if you put it all together. And if we call those three green lines asymptotes 1, 2, and 3, I would say asymptotes 1 and 2 belong to that box in red. Asymptote 3 belongs to the next one. Another thing you'll notice about secant and cosecant is the range isn't all real numbers. For tangent and cotangent, it is. The range is all real numbers. But how come the range isn't all real numbers here?
Because you're not hitting zero.
Yeah, you never hit 0. The only way for something to hit 0, think about this as a fraction. What's the only way for a fraction to ever equal 0? Yeah, the top is equal to 0. And in the graph of secant, the numerator is a 1. So these graphs never hit the axis. In fact, they never go between -1 and 1.
They do hit -1.
They do hit -1.
They just don't go past it.
They just don't go past it. Because think about cosine. Cosine is always between -1 and 1. That's my tick mark. Well, if you take a number that's between -1 and 1 and put that in the bottom of a fraction, you can get bigger and bigger numbers. Like if you divide by 0.5 or 0.2, but the only way you can get a number between -1 and 1 is if this denominator could be a number like 3. Then 1 divided by 3 would be 1/3, but it can't. Cosine never hits 3. So you're never going to get a fraction less than 1 between 1 and -1. So there's a gap. And that's secant and cosecant. Now, to find the period of secant and cosecant, I think I already said it. It's the same formula as sine and cosine. It's 2 pi over b. Now, we're not really dealing with b being negative, but if b was negative, we would take the absolute value because period is a distance. We would not want negative distance. So I don't think you're going to have to worry about negative b's anyway. So it can be a little tricky to try to remember like what the asymptotes are for tangent, cotangent. Wait, is this the one where it's odd multiples of pi over 2? Or is it the ones where it's the multiples of pi? So I have a table that puts everything in the same, puts it all on the same page. So what I've done in this table is I've given you one of the original asymptotes. So if you ever have to find the other ones, you can base all the other ones off this one. So for tangent, it's pi over 2. For cotangent, you can base everything off 0, because that's where the first asymptote for cotangent is. It goes right through the origin. It doesn't go through the origin.
Sorry, what did it say about the gray box?
For secant, the first 2 asymptotes that you will hit are the first 2 places where cosine cross the x-axis. Pi over 2 and 3 pi over 2. And for cosecant, it's going to be the first 2 places that sine would cross the axis. what are the first two x values of where sine crosses the x-axis?
0
Yeah.
and pi.
0 and pi. So you can figure all these out. It's just easier if you have a chart and you don't have to think about it as much every time. But those are all the original asymptotes for each trig function. Tangent, cotangent, secant, cosecant. Now, how do you get the new ones? Well, you would have to find one of the new ones first. How do you find one of the new ones? You set the old one equal to the argument and solve. We already had directions for that. So this x1 comes from doing this. Set the original asymptote equal to the argument and solve. But now you don't have to think about what the original asymptote is. You got a table. You could look it up. And once you find one asymptote, you always put plus the period times n. And that's the same for everyone. Plus period times n. For tangent and cotangent, you only need to worry about one asymptote per cycle. For tangent and cotangent, there are two per cycle. I'm sorry, secant and cosecant, two per cycle.
Oh.
So I'm not sure if there's really an easy way to memorize the original asymptotes. I don't know. I honestly don't have them memorized, so if you asked me what the first positive asymptote for tangent is, I would have to think of it quickly in my head like this. Say, okay, it's sine over cosine, and then I would think where cosine crosses the x-axis the first time, pi over 2. As long as you know about sine and cosine, you can figure this out. Okay, does everybody have the table? So this is a question that doesn't even have any transformations in it, just asking you about the basic secant function. Let's put the graph of it up so we can look at that kind of while we're doing it. All right, how would I put secant in on the calculator?
1 over cosine.
1 over cosine. And let's set the window from 0 to 2 pi. This should give us an idea of the period. How many U-shapes are we looking at in total in that picture?
2.
One,
What, you or-
two.
One U-shape,
Yeah.
and then how many of the N shapes?
1.
One. So this is one full cycle. So that tells us that if that window is 0 to 2 pi, and you're seeing one full cycle, what's the cycle length of secant?
Either pi or 2 pi, I don't know.
Isn't it 2 pies?
2 pi.
Okay.
Because it starts at 0, it ends at 2 pi, and you're seeing one complete cycle from 0 to 2 pi. So the period is 2 pi. Okay, let's do the range. To find the range, we know that there's a gap in the middle. We would need to figure out how low the U shape goes, and then how high the N shape goes. But I think we already kind of talked about that. It's everything except -1 and 1. So how would we describe, instead of what it isn't, what it is.
Negative infinity, comma infinity, or no, sorry, comma negative 1.
Close bracket.
So that describes everything from here down. Now I need here up.
1 close bracket. 2.
So there's your range. So we've got the domain. Well, no, we don't have the domain yet. Let's do the vertical asymptotes. And don't even think about the chart. I mean, you can if you want, but think about secant. What is secant? 1 over, it's 1 over cosine. And where's the first time cosine crosses the x-axis? There you go. So there's your vertical asymptote. I find it easier to think of it that way as you try to memorize the table. So our first asymptote is at pi over 2. And how often does that asymptote repeat? Every, it repeats every cycle. So there's 2 different asymptotes per cycle, right? There's one here. Let's call that, it's not very straight. Let's call this the black asymptote, and let's call this the red asymptote. The black asymptote is going to repeat itself every 2 pi units. Now, let's figure out the red asymptote. Think of cosine. When's the next time it crosses 0? 3 pi over 2. And how often will the red asymptote repeat? Every 2 pi. Now, there is a little fancier way you could write this and merge it all into one statement. Because this is repeating every multiple of 360 starting at 90. This is repeating every multiple of 360 starting at 270. So if you were to write that out, you'd notice a pattern, and you could write this a little bit compressed. But we're describing each asymptote separately rather than together. That's fine. Okay, so we've got the period, the range, the vertical asymptotes, the domain. Well, the domain is really everything except what? Yeah, it's everything except the vertical asymptotes. So everything except the vertical asymptotes.
How would you write that? Like
More numerically?
Yeah.
You'd have to write everything except numbers of the form, and then write down these 2 formulas.
Oh, I see.
Pi over 2 plus 2 pi n, and 3 pi over 2 plus 2 pi n. So it's everything except these numbers. Like this? But you could write it either way. So it's everything except the vertical asymptotes. And that was just secant. No transformations, nothing to it. Now let's look at cosecant. How would I put that in on the calculator? Yep. The answers here are going to be almost identical, except for one of them. But I think everything else should be the same. Okay, so there's 0 to 2 pi. That's your full cycle. What is the period? Yep, 2 pi. How about the range compared to the last problem? It's the same. So I'm just going to write same as example 3. So range is the same. Okay, vertical asymptotes. Those are different. Cosecant is 1 over sine. What's the first time sine crosses the x-axis? 0. Plus any multiple of the period. And what's the second time that sine crosses the x-axis? Pi. Here's the one at 0. Here's the one at pi. That's the only thing that's different. Period's the same, range is the same, vertical asymptotes are different, but then you could say the domain the same way, everything except the vertical asymptotes. Everything except vertical asymptotes. Question on? So most of what we do with these graphs is you don't have to actually sketch anything by hand. It's mostly describing like what's the period, what are the asymptotes, show me a graph with 3 cycles on the screen, things like that. Okay, so find the period and the asymptotes and show a complete graph of 2 cycles. Okay, let's start with period. Now this time I don't want to kind of think it through. I just want to use the formula that gives me the period. What is the formula for finding the period of cosecant?
2 pi.
Is it 2 pi over b or pi over b?
Just 2 pi.
It's 2 pi over b. Yep. What's b in this case? 3. That's important because that's what you're going to add to each asymptote. That's how often they repeat. Okay, asymptotes. How many asymptotes do we have per cycle? 2. Let's call them the first asymptote and the second. Actually, I'll do them like this. I'll write them as equations. X equals, because they're vertical. Okay, I need to hold off on that for a second because I need to do a little work off to the side to figure these out. Cosecant is 1 over sine. What's the first time sine crosses the x-axis? 0. So there's your first one. And what's the second time it crosses?
Pi.
No. 2 pi would be the same as 0. Pi. And what are we supposed to set each of those arguments equal to?
Set those to the argument.
Yeah, set those to
Yeah.
So set each of those equal to the argument, and that's going to tell you what happens to the original 2 asymptotes, and then we just write down that those repeat. So the asymptote that was originally on the y-axis, if you compress it 3 times as much and it's at 0, what does it become? It's still 0. So that's going to stay at 0. How about the asymptote that was at pi? If you compress that by 3 times as much, it becomes pi over 3. These are the 2 new asymptotes. So we need to write down 0 and pi over 3. And how often does each one of them repeat?
Every 2 pi. 2 pi over 3.
Every 2 pi over 3. That's the new cycle. So this one's going to repeat every multiple of 2 pi over 3. And so is this one. And again, there is a little bit more efficient way to write that, but we're describing each asymptote separate rather than together. Okay, so period, asymptotes, and do a sketch. This is on the calculator. Okay, how am I going to type in cosecant 3x? Yeah?
3 multiplied by 1 over sine.
That would be 3 cosecant x. So that would be a vertical stretch by 3. Yeah?
1 divided by sine 3.
Yep. 1 divided by sine 3x. Now, how many cycles do they want me to show? 2, so two periods. And that means my screen has to have a width of 1.
4 pi. No, just 2 pi.
Nope, not 2 pi, not 4 pi.
Yeah.
Okay, so it wouldn't have to be 2 pi or 4 pi. Think about what 1 cycle is, and we want to see 2. Yeah? 4 pi over 3. So 4 pi over 3. Now we're looking at cosecant, that's the U shape and the N shape. So 2 full cycles should be 2 U's and 2 N's. Let's see. There's a U shape and an N shape. There's 1 cycle. U shape, N shape. There's your second cycle. Perfect. So all I have to do for that is just show me what window you used. Okay. Questions on? Yeah.
How did you get the pi equals 3x and the pi over 3 equals x? What was that and how did you get it?
So this and this are the argument. So we set the argument on one side, and then on the other side is the original asymptotes.
Okay.
These are the 2 original asymptotes. If you go back to the table with cosecant in it, 0 and pi are the first 2.
Okay, that makes sense. Yeah.
That's where the 0 and pi came from. And then you take each of those asymptotes, where did I write it? And set the original asymptote equal to the argument, and then solve. And that's what we do.
Oh, so 0 equals 3x and the pi equals 3x.
Yes.
Okay.
Yep. Okay, so let's finish up with something we've done before, solving trig equations on the calculator. Remember, if you can find at least one solution, then that really means there's how many? Infinite, right? So if you've got a line going through a wave, and you say, well, yeah, I see at least 2, but if the wave and the line continued forever, it would be infinite. So if you can find at least one, then that means there are infinitely many solutions. How often, if you find a solution, how often is that solution going to repeat itself? Every period. So all you have to do is find one solution and then plus the period times n. Remember, n is an integer. So now instead of describing just one answer to the problem, we're describing every answer. We're going to find one and say that that one repeats itself every cycle forever. But you do need to find all the answers in one cycle. So if you have a problem like this, how many answers are there per cycle in this problem? 2. So you have to find this one using intersect, and find this one, and then say that each one of those repeats every cycle by putting this on the end.
We've already discussed this.
We've kind of already discussed this, yeah. We've just never had to solve a trig equation with a secant or a cosecant. We did it with sine and cosine on the last test. So let's try a cosecant. Well, even if you don't graph it, think of a cosecant, right? It's U shapes and N shapes. And you're going to draw a horizontal line. How many times is a horizontal line going to hit, no matter where I put it in this picture? Unless I put it right in the middle, then it could miss it. But that negative 1.6 isn't right in the middle. Twice. It's going to hit twice. So let's put this in. So we have 1 over sine in y1. What would I put in y2?
Negative 1.6.
And now it's very important that we set the window to be one cycle. So what's the period of cosecant x? Okay, so let's go 0 to 2 pi. If we set it too big, we're going to get more answers than we should. If we set it too small, we might lose some. We need exactly one cycle. We're going to have a horizontal line at negative 1.6. Okay, so there's our graph. And what do I need to do now? Find the intercept. So second calc intersect. So sometimes you might go off the screen because it's in two pieces. If you're on the top piece, just hold right until you get to the bottom piece. Okay, I'll do the one on the left. If somebody gets the one on the right, that would be good. So 3.82 plus, how often is that going to repeat specifically in this problem? It's going to repeat again 2 pi units later, and then another 2 pi units after that, forever. And the second answer.
5.61 plus 2
Plus 2 pi. So by adding the 2 pi n, you have described every single answer in this problem forever. You described them all. Okay. Let's finish up with tangent. Now think about what tangent looks like. That one looks like this. If you put a horizontal line through that, how many times is it going to hit? Just once. So we're going to put in tangent. I'm going to put in 2.5. Is there anywhere that I could put a number where it would not hit tangent? No, because the range of tangent is, it's all real numbers, yeah. So no matter where you put the number, it's going to hit it somewhere. Okay, set your window to one period. What's the period of tangent? Pi. So we should see exactly one cycle. It might break it into two pieces, but that's still one cycle. Just half and half. All right, so second calc intersect. Oh, I must have did the wrong thing. Second calc intersect. I didn't move my cursor. So I get 1.19. And when's the next time that answer is going to occur? How many units later? Yeah, pi. If you add 3.14 to that, that's the next answer. And again, and again. Okay, so not as much graphing by hand, and that finishes up everything that we're going to do with graphing trig functions for now. Any questions on that? So that's the homework for tonight. Okay, on 352. I think overall this is probably the hardest section for this week. 6.5 is 6.5. I think you'll find it a little easier, especially if you've done opposite adjacent hypotenuse before.